So all this talk of efficiency leads us to discuss big O notation. Big O notation tells you how fast an algorithm can run. So, for example, finding the largest of n numbers. Well, you only have to pass through the list of numbers once, and you just compare each one to the largest one you've seen so far. So we call this algorithm can be run in O of n time, meaning it's proportional to the number of numbers in the list. As opposed to sorting a list of n numbers, and those of you who have programmed before have studied this, there's lots of ways to sort, but like the most terrible way is bubble sort, where you start at the beginning of a list. Here's your list. You look at those two. If they're not in order, you swap them. And then the next one, you look at those two, and if they're not in order, you swap them, and so on. And first pass through the list, you're not going to get everything. But you will get the largest number at the end. So next time you can go through and do the same thing again, but you don't have to touch the last one because the largest number is already at the end. And then same thing, you do everything, you don't have to touch the last two, and so on. Okay, so this bubble sort is very, very inefficient. This is O of n squared. You're basically going through the list n times, and each time you're checking n things. It's really more like n choose 2, because you stop a little bit earlier every time, but we don't care so much on big O notation. It can be imprecise, so we just say O of n squared. Whereas there's a better algorithm, which I'm not going to explain, called quicksort. That's still, so programmers talk about worst case and average case. Worst case, it's just as bad as bubble sort O of n squared. But on average, it's a lot faster. This is O of n log n. Log n way better than n. Okay, so quicksort is great. And then another example is solving a system of n equations using Gaussian elimination. That's in matrices. You get it into row reduced echelon form. That is O of n cubed. It takes a little bit for each entry. Okay. Then we look at the traveling salesman problem. And we already know this one because we looked at that brute force number of ways. This is O of n factorial. Okay, so the great thing about all of these things up here is they can be solved in what we call polynomial time. All of these things are polynomials. N squared, n log n is smaller than a polynomial, smaller than n squared, n cubed. You can have n to any power. You can add things up. That's polynomial time. The traveling salesman, n factorial is not smaller than any polynomial. So traveling salesman cannot be solved in polynomial time. Polynomial time things are good, not polynomial time things are bad. Traveling salesman, however, can be solved in what we call non-deterministic polynomial time. We call this P for polynomial time. We call this NP for non-deterministic polynomial time. Maybe you've heard of these terms. So what does this non-deterministic polynomial time mean? It means that the problem can't be solved in polynomial time. You cannot find the shortest path for the traveling salesman in polynomial time. We know this. But we can verify in polynomial time. This is actually non-trivial for the traveling salesman problem, but the claim is, given a path, we propose a path, we can verify whether that is the shortest path in polynomial time. And we're not going to get into the algorithm for traveling salesman to do that, but that can be done in polynomial time. Here's an easier to check example that's also NP, non-deterministic polynomial time. The problem is, given a set of integers, is there a non-empty subset of those integers whose sum is 0? So can we pick some of them, add them up, and get 0? That's, again, very hard to do by brute force because all the subsets, there's actually 2 to the n subsets if there's n integers. So exponential time to completely solve it. But if you give me a subset, it's really easy to verify whether the sum is 0, just add them together. That can be done in actually the size of the subset. So at most n, definitely polynomial time. Okay, that one we know for sure. Non-deterministic polynomial time. And the very, very famous problem in computer science is to decide whether p equals np. It seems like they shouldn't be. It seems like the non-deterministic polynomial time problems are harder than polynomial time problems, but we cannot so far prove it either way. It is possible that any non-deterministic polynomial time problem can actually be solved in polynomial time. So we're looking for a proof of that either way. The Clay Mathematics Institute offers $1 million currently. Actually, I think that will stand forever. It's one of the 7 millennium problems, only one of which has been solved, the Poincare conjecture. Everything else is still open. This one probably has the most profound implications. So if you're interested in this, you can go ahead and get working on it. Claim $1 million. The other cool thing about the traveling salesman problem is that it's NP complete, and so is that problem where, given a set of integers, is there a non-empty subset whose sum is 0? NP complete means we can reduce it easily to any NP problem. So what's great about this class of problems, and there's a long list, people have been adding to it for a long time, of NP complete problems. Basically, if you solve one NP complete problem, you've solved all of the NP problems. So that's pretty cool. And also, if you prove that one of them can be solved in polynomial time, then you've proved P equals NP.